So in the previous discussion, we introduced the concept of the Sagittarius representations. In this section, we're going to work through a specific example and see how the whole thing plays out in terms of constructing the set of 27 elements in the molecular tensor from the set of arrows. And so let's look at this case as one example. So we're given this Sagittarius representation, assuming everything interesting is happening in the x prime, y prime plane. There are no significant z prime contributions. And the question is, what are the non-zero elements in the molecular hyperpolarizability for vibrational sum frequency generation from this set of arrows? And so the way you do it is, the first thing you need to know is the magnitudes. Let's look at the transition moment first. If that scale bar is 0.1 atomic units, then that's about 0.1 atomic units, and that's about roughly another third. So let's say the magnitude is going to be it's going to be 0.13 AU times, and then the question is, what are the non-zero elements? And if we look at this, we're going to project onto y and project onto x. The projection onto x, if this is our, well, 39 degrees is that angle, right? So the projection onto the x-axis is going to be given by negative sine 39 degrees. And the y projection is going to be cosine, which I hope that's what we get. It's much easier to see if I erase this now. Yeah. So we get a value of negative 0.08 times for the x contribution and 0.101 for the y contribution. So that gives us our transition moment components right there. We'll do the exact same sort of approach for the Raman matrix, where we'll project all the different elements onto what's a little bit harder to do the projection in this case. What really turns out to be more convenient is to generate alpha in this reference frame where we know what the magnitudes of the elements are. So I'll define here a new x, y reference frame. So in this x, y reference frame, I only have alpha xx and alpha yy, right? So we can, based on the magnitudes, I guess I've done this differently. Let's do x, y. Okay. So in this xy reference frame, x is large with a magnitude of 2.4 based on the length of the vector and the scale bar. So that gives us this 2.4, that's the blue line here. And then the red tells us that the y component is smaller and negatively signed, and if we scale it appropriately just with a ruler, we would do the trick, then we get that for the contribution for the y in this principal coordinate system. So how do we get from the principal coordinate system to the x prime, y prime coordinate system? Well, there's a couple of ways we can do it. We can say alpha prime equals r 68 degrees times negative 68 degrees times alpha times r 68 degrees, which is a coordinate system reference frame rotation. Or we can vectorize alpha and say that alpha prime vectorized is equal to r 68 Kronecker r 68 times alpha vectorized. So in vectorized notation, or either way works for this particular case. You can either rotate the matrix or you can vectorize and rotate the vector. In either case, we get the same result either way. So now what? Oops, that's not what I wanted. Let's try. Okay, this is really getting fun here. Let's try erasing all of this. And that gives us this expression for the rotated elements in the transition moment for alpha. So this is all now in this x prime, y prime coordinate system. All right, so that's good news. Now if we just combine everything, what does that look like? How do we combine it? Well, we know that for vibrational sum frequency generation, the vectorized beta, all 27 elements in a row, is given by the vectorized alpha, Kronecker producted with the vectorized mu. And that turns out to look like this. That doesn't look like 27 numbers, does it? It's not, because we're only in the x prime, y prime coordinate system. We've neglected anything with a z in it. So we should only end up with 8 in this reference frame. Everything with the z is 0 valued. We can populate the full set of 27, but in this case only 8 are relevant. All right, so that's sort of the general architecture for how you take the Sagittarius representation and then invert it to recover all elements, all non-zero elements in the molecular hyperpolarizability in any x prime, y prime reference frame. Well, that's all well and good, but it turns out we can't use Sagittarius representations for describing every interaction. Specifically, they work only when you were talking about individual chromophores and individual transitions. Now, this is unfortunate, but one of the sad facts of life. And the reason is that it's really based on this molecular description for the resonant hyperpolarizability, resonant nonlinear polarizability in terms of alpha and mu. So if we have an ensemble of many betas, then the same representations cannot be used. So that's a big limitation of this visualization approach. It really only works at the level of single molecules. Now I'll just say very briefly something about a computational package that's out there to make visualization a little bit easier to deal with. And this is NLO Predict. And if we just go to that, I can show you how that works. So if we go to NLO Predict, here's an example of a molecule. This is actually the primarily carbonyl stretch in the amide unit connecting two amino acids in a protein. This is just a simplified model for the nonlinear optical properties of that linkage. And you can see that this double-sided arrow, we can move the system around in any reference frame. And if we choose a reference frame like this, so to give yourself a sense of reference frames, horizontal. The horizontal axis is the x-axis, the vertical axis is the y-axis, and coming in and out of the page is the z-axis. We can describe this particular molecule in any reference frame just by moving it around. And so if we look at one that has the coordinate system such as shown here, what do we expect? We expect it's going to have a big y component because there's a big projection of the transition moment on the y-axis and a large Raman polarizability on the y-coordinate. And that's exactly what we see right there. So what we're generating with this system is consistent with expectations. Nice big y component when we rotate it appropriately, and we can suppress other things if we get it oriented just so the plane of the molecule is lying in the plane of the xy plane. And so this allows us to very intuitively and simply describe the full set of 27 numbers in any reference frame and relate those back to the Sagittarius representation.